everyone. Welcome to the online course on matrix method of structural analysis. This course is being offered as NPTEL online certification course. So, let us begin by acknowledging NPTEL for this great initiative and also Center of Education and Technology IIT Kharagpur for making this arrangement. Okay, to start with, let me introduce the team here. We have there are two instructors for this course. My name is Amit Shaw. I am a faculty in Department of Civil Engineering, IIT Kharagpur, and along with me, Professor Vishwanath Banerjee, who is a faculty in the same department, will be taking some of the lectures. Well, if you have enrolled for this course, then you have access to the discussion forum, and throughout this course, you can post your queries in the discussion forum. But if you have not enrolled this course, you have just attending this course, then you can or those even after this course is over, even after that as well, if you have any clarification, anything to discuss, then you can always write to us. You are most welcome to write to us, but please make sure whenever you write to us, the subject of this email should be NOC-MSA. This will help us to identify these emails among all the emails that we get regularly. Okay, so this is the first class on introduction. See, this is an intermediate level course. So, there are two important prerequisites for this course. One is matrix algebra, and I am sure that all of you are familiar with matrix algebra. If not the entire algebra, some of the concepts of matrix operations, then properties of matrices, and solution of system of linear equations, linear algebraic equations. And as this is an intermediate level course, a second level course, so it is assumed that you have already done the first level course on structural analysis, which is structural analysis 1, and for the completeness of this course, we will be spending some time, initial few weeks, to revisit some of the basic concept of matrix algebra and structural analysis. But don't wait for that. Please go back to your basic, go back to any structural analysis book or matrix engineering mathematics book to brush up some of the concepts, basic concepts in these two subjects. Okay. You see, if I have to, this course is for 20 hours spanning over 8 weeks. Throughout this, as we go through this journey, we'll learn what is the matrix method of structural analysis and how the matrix method of structural analysis can be applied to different kinds of structure. But since it is the first class, let us try to understand what is the motivation for this method. Why the knowledge of structural analysis 1 that we already have are not sufficient to analyze the structures that we come across in everyday life. So, in this lecture, we will try to find out a good reason to learn matrix method of structural analysis, right. You see, if I have to define what is structural analysis, then probably in one slide, if I have to define, then this will be the definition. If we have a structure which is subjected to different kinds of threat, and then we want to understand how the structure may respond when they are subjected to different kinds of threat. And in fact, it is not only for structural analysis. If you look at carefully, you will see that any engineering analysis is based on this philosophy. We have a system, any system, and in this system, there is some input, and we want to understand what would be the corresponding output, right. Now, here input, here the system is structures, different kinds of structures, and input is threat, and the output is the response of the structure. Now, what are the different kinds of threat are possible? You see, if you these are the different kinds of threats that a structure may be subjected to. We can have dead load, which is the self weight of the structure, live load on the structure, then we can have earthquake load, then wind load, earth pressure, water pressure. If it is offshore structure, then wave and current loads are important. We can have blast load and impact load. Depending on the environment, we can have snow load as well, and other than that you can have support settlement, we can have thermal loads, we can have machine vibration, and so on. There are different kinds of load. So it depends on what is your objective, for which purpose you are building the structure, what is the purpose that the structure is going to serve. Depending on that, you have to consider the load, right? Now you see, once we have this load, then what are the structures that you have so far studied in structural analysis 1? You have studied how to solve, say for instance, a beam problem. It could be a say simply supported beam or continuous beam. You have studied how to solve the frame problem, say. Then you have studied, say, if you have a truss, then you have a truss. So these are some kind of structure that you have studied how to analyze these kind of structures. Okay. And the response, what response we have studied so far? Now if these are the structures subjected to the threat, again, as I say, there are different kinds of threat, but at the end of the day, you can see that threat can be idealized as some concentrated load. For instance, in this could be say these structure are subjected to uniformly distributed load or concentrated load, or you can have a concentrated moment. You can have a different kinds of load. Say these are different kinds of threats. Okay, and these are some structures, and what we have studied, what response we have studied so far, we have seen how to calculate, say, bending moment diagram. If it is beam, then what will the bending moment diagram means at any particular section, what is the bending moment, and at any particular section what is the shear force from the shear force diagram. And then we also have seen how to find out axial force diagram. At any axial force diagram, at any section, what are the axial forces, the internal forces in the member. And in addition, we have seen support reaction, how to find out support reaction, and then we have seen how to find out say displacement. So these are some responses that we have you have studied in structural analysis 1. Okay. Now you see, this analysis is there are some steps followed in any engineering analysis, and so is for structural analysis. And what are those steps? Those steps are, say first we have a physical system, and that physical system is the actual real system that we want to study. But you know, because of many reasons, because of the complexity associated with the system, complicated boundary conditions, and there are some uncertainty that we don't know, we cannot take the physical system as it is. So what we need to do is, first we need to idealize the physical system. So first step we idealize the physical system, simplify the physical system. But your idealization should be based on the physics of the system. The idealization should be based on the what kind of analysis you are going to do with the system. And you're at the end of the day giving all this, given a particular objective, your idealized system should be as close as possible to the real system, the physical system. Now once you have idealized the system, next we represent the system, idealized system, through some mathematical equation. That is the mathematical representation of the idealized system, and that mathematical representation could be in the form of, say, algebraic equation, differential equation, integral equation, or combinations of all. Now once we have the mathematical representation of this idealized system, next step is the solution of this mathematical model. Now please remember, one thing is to be noted here: at every steps, like from physical system to idealized system, and then idealized system to mathematical model, and then solution of the mathematical model, at every steps we assume something, we make certain assumptions, and these assumptions are very important because these are the assumptions which are the limitations of this flow as well. Because suppose if any theory or any methodology is based on certain assumptions, it is very important to understand those assumptions, because the limitations of that methodology are the assumptions. The cases where those assumptions are not valid, those cases this method cannot be applied. So, it is very important to understand those assumptions. Okay. Now, just to give you an example, so this is the starting point of any analysis. The truss, the frame, the beam that I just that I shown in the previous slide, those are all idealized system, not the actual system. Right. Now, let us give you an example. Take a physical system. This is a cantilever portion, cantilever slab at the front gate of a structure. The entire structure is not shown here because of the space. Now, suppose I want to analyze this cantilever portion, this structure. Now, what would be the idealized? This is the physical system. The idealized system will be this entire thing can be idealized the cantilever beam, which is subjected to uniformly distributed load, and the uniformly distributed load is the self weight of this beam. Now, once you have idealized the system, the mathematical representation, if you recall the mathematical representation that you used here in solving these kind of structures in your structural analysis 1 course, that is the equilibrium equation, and then compatibility equation, and of course, the boundary conditions. Okay. Now if you use this, once what is equilibrium equation? This equilibrium equation says that the internal forces and external forces, they should balance each other, right. Compatibility boundary conditions here is what? For instance, at this point, take a different color. At this point your displacement is 0, u is equal to 0, u is equal to 0, and the slope is equal to 0. So, dy du dx is equal to 0. These are the boundary condition you have here. The slope is 0 and moment is 0, right. And then equilibrium, if you use this equilibrium conditions, if you remember, summation of forces is equal to 0 and summation of moment is equal to 0, right. Now, these are the equilibrium conditions. Now, if we apply these equilibrium conditions, then the bending moment diagram for this beam will be something like this. This is the bending moment diagram, and the shear force diagram will be linear, something like this, and the deflected shape will be something like this. So, we already know with the knowledge of structural analysis 1 how to get this solution. So, these are the solution of the equilibrium equation, compatibility equation, and boundary conditions. Okay. Now, you see, so that we do for all the structure. Now, let us so this is the starting point of analysis. Now, you see, let us find out now, before, as I say, since this is the first lecture, the idea of this lecture is to find out a good reason to learn matrix method of structural analysis. Just the flow that I have that is shown here, that this flow we know how to do this, how to solve this structure with the knowledge of structural analysis 1, right. Now, let us find out why this knowledge is not sufficient to solve to deal with structure that we come across most of the time. Now, instead of directly coming onto the motivation, let us try to understand the motivation through some examples. Now, you see, take one example. This example, we are going to take a few examples. That examples are you have seen this kind of example in your school physics or your first year engineering mechanics, or even some of the examples that you have not learnt in your engineering curriculum, but you can relate to those examples because you have seen them many times. Suppose this is an electrical circuit, right. Now, what we want to do is, So these are three resistors, one R1, R2 and R3, and then we have to find out what is the this if the current is I, then we have to find out what is the voltage output V. Okay. Now you see what we, if you recall how you solve this example, we have three resistors, this is three resistor, this is three resistor R1, R2, R3. Now then what we can do is we can write here that V1 is equal to, for this V1 is equal to I1 I plus I R1. This is the relation, right? From Ohm's law we can get this relation. Similarly, here we get V2 is equal to I R2, and similarly here V3 is equal to I R3, right. So this gives you the voltage drop across this circuit, this gives you voltage drop across this resistor, and this gives you voltage drop across this resistor. Now the total voltage drop is V1 plus V2 plus V3, which should be equal to V. Then we have V is equal to V1 plus V2 plus V3, and if we substitute V1, V2, V3, this gives us the effective resistance R S, or resultant will be R1. You know this, so I am not writing the entire steps here. Okay, R3. Okay, so this can be can have a system like this, where this is RS and this is I and this is V. Okay. And then we have V is equal to I into RS, when RS is equal to R1 plus R2 plus R3. So there is, as an example, there is nothing to see new here. You have already seen it, but my objective here is not to solve this electrical circuit problem. My objective is something else, and that will be clear shortly. Now, before we come to that point, let us see one more example. This example is, again, you have seen in your first year mechanics, I believe. That is a spring network. We have three springs are connected, K1, K2, K3, and they are connected in series, and there is a force F being applied at the end. Now, what we want to know, K1, K2, K3 are the stiffness, spring stiffness of respective springs. Okay. Now, if we apply a force F like this, suppose the springs take a form this, and the deformation in the total deformation becomes X. Now, let us find out. Let us try to find out a relation between this X. Relation between this X and the and F, right. Now, what we can do is, before we first we take, and if you this also you have seen in your first year mechanics, we take these three springs separately, spring 1, spring 2 and spring 3, and then at any point if we take, the force will remain same, F. So, suppose x1 is the displacement here, x2 is the displacement here, and x3 is the displacement here. Then we know here that F is equal to K1 x1, and similarly F is equal to here K2 x2, and here F is equal to K3 x3. We know that, and total X will be x1 plus x2 plus x3, and if we substitute that, and for this spring, if we have to find out a relation between F and X, we have that F is equal to Ks into X, where Ks is the effective or the resultant stiffness of the spring system, and Ks is related to K1, K2, K3 as this. Ks is equal to, and 1 by K1 plus 1 by K2 plus 1 by K3. Again, please note an inverse, right. Please note here idea has not been to solve this problem. Again, my objective is to make a point, and again before coming to that point, these are the examples that probably you can relate to these examples if you are an engineering students. Let me give you some other examples. You see, so this is an example. You don't suppose I want to make a shirt. This is the thing that if you go to any tailor shop, they do. This is the final product, and this final product, in order to make this final product, what tailor does is tailor makes few cut pieces like this. Okay. And these cut pieces are not random cut pieces. These cut pieces are with proper measurement, right? And then once we have these cut pieces, then what tailor does, they stitch all these cut pieces together and get this the entire shirt. So all these are stitches together to get this, right? Now again, before I make the point, let me see one more example, and the example is, you see, suppose this is a typical passing pattern in football. So take one more example. This is the last example before we make the point. This is a typical passing pattern in football. You see, the objective is to from position A, objective is to pass the ball to different fielders in such a way that we can make the goal. Okay. Now you see all these passing patterns are shown and the movements are shown by arrow. One is dotted arrow, passing pattern, and the bold arrow are the movements of player. Now you see, if we follow these and all these passings are numbered 1, 2, 3, 4 and so on, and here it is given these A, B, C, D are the different players, and it is shown that how the ball should go from one player to, in which order the ball should go from one player to other player, and this is the orders, and this is the way the ball should go. Now in order our objective is to make the goal. But what is done here is, instead of making the goal just directly, a path is followed, right? And if we follow this path, if we add the entire path, then the objective can be accomplished, right? Now let us see the example. All these examples, and there are plenty of examples in nature, and every day we follow the similar approach. And what is the common thread between all these examples? All the examples are from different fields, they have different execution, they have different objective, but there is a common thread in all these examples. And what is that common thread? The common thread is, you see, remember in the electric circuit problem, there are 3 resistors. We broke the entire circuit and wrote the equations for each resistor separately, and then the conditions what we used is, total voltage will be V1 plus V2 plus V3, right? And that condition when we apply, that gives the resultant resistance as Rs is equal to R1 plus R2 plus R3. Similarly for the stiffness problem, the spring problem, we broke the entire problem into 3 parts, 3 spring parts, wrote equation for each spring. What are the equations? F is equal to K1 x1 for spring 1, F is equal to K2 x2 for spring 2, and F is equal to K3 x3 for spring 3, right? Now, and then these are separate equations for separate springs. then we wrote an equation, wrote a condition, and what is that condition? That total deformation will be x1 plus x2 plus x3, and that condition gives us what is the effective resistance of the entire spring. In the case of shirt problem, the entire thing, we have several cut pieces, and then those cut pieces are stitched together to get the final shirt. And here also the entire objective is broken into small steps. So what are those steps? Here the steps are passing a ball from one fielder to another fielder. Now if we follow all the steps, if we combine all the steps, then we get the final objective. The common thread in all these examples is this: if we have a problem which is very difficult to comprehend as a whole, because of the complexity of the problem, because of the complicated boundary conditions, or because of many uncertainties that probably we don't know about the problem. So this is a problem, and this is a representation of the problem. This problem could be the electrical circuit problem, it could be the spring problem, it could be the passing pattern problem, it could be the stitching of shirt problem, or it could be any other problem that we come across in real life. Now this problem we don't solve, we don't address. Our approach is what? Approach is not to analyze the entire problem together. Instead, the approach is we divide the entire problem into small sub problems, say P1, P2, P3 and so on. Okay, and then now you see the entire problem. Initially this shape was complicated shape. Suppose in this case the problem is to find out the area of this shape. These are very complicated shape. So what we do is we divide the entire area into small areas, small triangular areas. Now for each triangle we know how to determine the area, right? Now then, so this is the division of the decomposition of the problem. This is also called discretization of the problem. Then these are the different sub problems. We write equations for each sub problems. Now these problems could be when it is a problem of electrical circuit. So these P1, P2, P3 they were the each register separately. When it was a spring problem, P1, P2, P3 were the springs, individual springs. When it was stitching a cut piece, stitching a shirt problem, then P1, P2, P3 were the different cut pieces. And when it was passing pattern, making a goal, then P1, P2, P3 were the passing a ball from one fielder to another fielder. And so these P1, P2, we divide the entire problem into small sub problems such that for each sub problems we know the equations. We know how to represent those sub problems through mathematical model. We know how to represent each register V is equal to IR. We know how to represent, what is the relation between stiffness and the displacement of individual springs. So we can write equations for each sub problem, and then once we write the equation for each sub problem, what we did, we in the case of electrical resistor problem, we wrote V is equal to V1 plus V2 plus V3. In the case of spring problem, it was x is equal to x1 plus x2 plus x3. Means we give a condition to all these. We give a condition which says how these different sub problems are connected with each other, how these different sub problems are related to each other, right? So in somehow if we can relate these individual sub problems with each other through again an equation, and then you solve that equation. So these constitute the premise of matrix method of structural analysis. Not only that, the advanced structural after matrix method of structural analysis, the more advanced course on finite element, advanced course finite element method, the premise is exactly that. So as a philosophy, the matrix method of structural analysis, the philosophy that we use, that philosophy we have used many times. Not only engineers, anyone. If you carefully think in day-to-day life also, in some way we follow this philosophy. Break the problem into small pieces, small sub problems. such that for each sub-problems we know the information, write equations for each sub-problems and write a conditions how these sub-problems are related to each other, and then that condition gives you the solution of the entire problem. So, that is the philosophy of matrix method. Now, you see that philosophy, why this is required, because if you see the real structure, these are some examples of some famous structures. I have not given the names of the structure because I believe these structures are so famous that names are not required. Now, if you look at the structure, they are not just a beam, they are just not a portal frame or a simple plain truss. There are members oriented in a different configurations. There are thousands of members connected with each other. Those kind of structures cannot be solved just with the method we studied in structural analysis 1. So, what we have to do with these problems, if you want to analyze this problem, what we have to do is we have to follow the philosophy that just now we have seen. We need to break the problem into small sub problems and then assemble all these sub problems to solve them. Okay. So, if we have a truss like this, what we have to do is, this is the philosophy of matrix method of structural analysis. We break the entire thing into small problems. You see small problems, and then write equations for, you write equations for this, write equations for this, write equations for every elements, you write equations, and then write a conditions which tells you how these elements are connected with each other, how these elements are related to each other. That writing that step is called the assembling. So, we assemble these information from each sub problem, we assemble them to get the information about the entire system. That is the basic philosophy of matrix method of structural analysis, and that is exactly we are going to learn in this course, how it is to be done, how to decompose into small problems, how the equations for each problems to be written, and how the assembling to be done, and finally once we have assembled it, then how the assembled equations to be solved. Okay, and everything we will do in using the concept of matrix theory. That is why the name is matrix method of structural analysis. Okay, so this course is this. Structural analysis is the foundation for this course. So, you already know the structural analysis 1. Then this course is a journey which takes you from structural analysis 1, and at the end this course will prepare you for more advanced course, more sophisticated, more elegant course, more general method is called finite element method, which also does the same thing, breaking the entire problem into pieces and assemble them, but in a more mathematically sound way, more elegant way, more sophisticated way. So, this is the course, this is the journey which will take you from structural analysis 1 to finite element method, and this is the week wise the lectures. As I said, the first 3 weeks, the first 2 weeks will be review of structural analysis 1, and then review of matrix algebra, some of the basic matrix operations, matrix theory on the 3rd week, and then from 4th week we will start formulating this matrix method of structural analysis, and that formulation will be demonstrated through trusses in the 4th week, and then through beams in 5th week, and the plane frame 6th week, space frame 7th weeks, and then finally when we know how to apply this matrix method of structural analysis for different problems, then 1 week will be spent to discuss how this concept can be taken further to formulate a method which is more elegant, more general, and that is on the 8th week we will have some brief introduction to finite element methods. Okay, as far the books are concerned, there are again many books. These are the books that you can follow, but in this course we will not follow any particular book. We'll solve examples from different books. Some of the examples will be listed in this book, some of the problems probably from somewhere else, but for reference you can see these books. Okay, and just before we stop, you see, when you are studying any theory, any method, it is very important. Learning from the history of that method is an integral part of your learning process, because we cannot comprehend a course, we cannot comprehend a subject, we cannot appreciate probably a subject in a comprehensive way if we don't know how the structure evolved over time. So, if you just Google history of matrix method of structural analysis, there are many articles you get, but one interesting article I suggest all of you must read is the article which was published in June 2000. It was the article published in College of Engineering, University of Colorado. That was the historical outline of matrix structural analysis, a play in 3 acts. The entire history of matrix structural analysis is told as a story in 3 acts. Okay, so it is an interesting read. Please go through that if you are interested. Okay, we stop here today. So next class we'll start revisiting some of the basic concept of structural analysis. We'll start with degrees of freedom, constraint, and static equilibrium. See you the next week. Thank you.